Formal charge. The formal charge of an atom, and we're going to talk about what formal charge is and why you want to do it and all that crap in a second. Hang on. The formal charge is equal on an atom is equal to the valence electrons. So the number of valence electrons minus the sum of the number of bonds that atom is making plus the number of electrons in lone pairs. So in other words, dots. Okay. The formal charge on an atom is equal to the number of valence electrons that atom has naturally minus the sum of the number of bonds that atom is making plus the number of electrons that atom has in lone pairs or dots. Okay, formal charge is a mathematical formula. We're going to calculate some formal charges here in a second, but let's talk about what the formal charges tell you. The formal charge on an atom tells you the formal charge on an atom tells you how happy the atom is atoms like to have a formal charge equal to 0, but that is not always entirely possible. The sum of every atom's formal charge must add up to the charge on the molecule or ion. Copy that down, we'll talk. Let's do this. Let's talk about it. Let's do it for a couple structures. Formal charge is going to be the real reason why that molecule COF2 was the way it is, but we're going to get to that in a second. Let's just calculate some formal charges on some Lewis structures. And let's start really simple. Let's not even do anything crazy. Let's not do any resonance. Let's just keep it simple, keep it cool. Oh man, let's do silicon tetrachloride. So SiCl4. Over the break, I'm going to go grab some more markers. I'm going to get another marker. They're in my backpack downstairs. Okay, here's what I want you to do. Add up the valence electrons, draw the Lewis structure for silicon tetrachloride. Then what we're going to do is we're going to calculate some formal charges. So all I want you to do right now, add up those valence electrons, draw the Lewis structure. You got this. So that's 4 plus 28 equals 32. Silicon in the middle. Down here. 4 chlorines coming off of it. Used up 8, leaves you with 24. Silicon's happy. It's got its full octet. If you're a thinker, each chlorine needs 6 more. 6 times 4 is 24. You're good to go. So you're going to do 3 lone pairs on each chlorine. Now, I picked this one because we really only need to do this calculation twice. Here's why. We're going to start with silicon. So I'm going to do the formal charge calculation for silicon. What's that going to equal? Well, it's going to equal the number of valence electrons that silicon has. Look at the periodic table. Silicon comes to the party with 4. So that's 4 minus the sum of the number of bonds silicon's making. Silicon is making 4 bonds plus the number of electrons in lone pairs on the silicon, not on the other atoms, but on the silicon. Silicon has no electrons in lone pairs. 4 minus 4, that silicon has a formal charge of 0. That's a very happy silicon atom. And now here's the beautiful thing. all four of these chlorines are the same. Each of the chlorines has a single bond with 3 lone pairs. So if I want to calculate the formal charge, that's 7 valence electrons for the chlorine minus the number of bonds it's making. Each chlorine is making 1 bond, plus the number of electrons in lone pairs. Not lone pairs, but dots. This guy's got 1, 2, 3, 4, 5, 6 dots. So this is 7 minus 7. That is 0. Each chlorine has a formal charge of 0. So 0 on the silicon, 0 on the chlorines. This is a perfect structure. Silicon tetrachloride is a neutral molecule. It has no charge. It's not an ion. So all of the formal charges have to add up to 0. 0 plus 0 plus 0 plus 0 plus 0 adds up to 0. Yeah, it's a happy molecule, right? Okay. What else? Everybody is as low as possible. 0 is as good as it gets. So this is a happy structure. Okay, this is like the happiest. Okay, let's talk about another one before we get back to the COF2. What to do. Let's do, all right. Let's do HCN. I want you to try to draw the Lewis structure for HCN, and then I want you to try to calculate the formal charge on the hydrogen, the carbon, and the nitrogen. All right, here we go. 1 for the hydrogen, 4 for the carbon, 5 for the nitrogen, 10 to work with. Hydrogen to carbon to nitrogen used up 4, leaves me with 6. Okay, what do we got? Well, a thinker says I need 4 plus 6, that's 10. I've only got 6, I'm short 4, 2 more bonds. A doer says 2, 4, 6, and it's a double. Uh-oh. What do you got to do? We got to add 2 more bonds to this structure. What's that going to look like? That's going to look like a triple bond. Right? Now we got 10 electrons. We just spent 2, 4, 6, 8. Leaves us with 2. That's going to be a lone pair on that nitrogen, just like that. By the way, I don't care where you put that lone pair. You put it on the top, you put it on the bottom, you can whatever, right? I'm going to pop it on the side. Now I want to calculate the formal charge for these cats and kittens. All right, so here we go. Hydrogen. Okay, number of valence electrons. Hydrogen brings 1 valence electron to the party, minus the number of bonds it's making, 1, plus the number of electrons in lone pairs, 0. That hydrogen's got a formal charge of 0. Carbon. Carbon, 4 valence electrons. It's got 4 bonds, and it's got no electrons in lone pairs. That's 0. And then nitrogen. Nitrogen, 5 valence electrons. I'm sorry, my neighbor's mowing. It's always mowing he's got a real job, over the summer is where, this is when he's home to mow. So not knocking him for that, but I just feel like it's always on a Monday or Wednesday when I'm like teaching. Anyway, 5 minus 3 bonds plus 2 electrons in lone pairs. That's 0. Every atom in this structure has a formal charge of 0. They all add up to 0, which is great because it doesn't have a charge. So there's my structure for HCN. Okay, now we're going to try this on a trickier substructure. Okay, and then we'll come back and talk about why COF2 really is the way it is, which is what we ended class on Wednesday. So I would like you to try carbonates. Okay, which is another one of those polyatomic ions you had to memorize. Here's what I want you to do. I'm going to tell you, this resonance, this resonance, this resonance. So I want you to add up the electrons. Watch out, it's a -2 charge, right? So you got to add 2 electrons, okay? Try and draw it. Try and draw all the resonance structures, and then don't do formal charge because I don't want you doing more work than you have to. It's not that much work. Okay, so here's what I want. I'm just telling you, it's a resonance structure. So I want the resonance structures. Yeah, add up the electrons, figure out how many electrons are short. Give me the resonance structures. Good luck. Then we'll do the formal charge, or at least I'll get you started on the formal charge. Let's see how you did, folks. We got 4 plus 6 times 3, that's 18. Plus 2, that's 24 electrons to work with. You pop a carbon in the middle, we got 3 oxygens coming off of it, used up 6, got 18 left. 2, 4, 6, 8, 10, 12, 14, 16, 18. Carbon's not happy. It's an uh-oh. You need to add a bond. But how do you add a bond? You can put it here, you can put it here, you can put it here. They're all the same. What do you do? The answer, all of them. So here we go, folks. This is some resonance. I'm going to put the double bond at the top first. The doubly bound oxygen gets 2 lone pairs. The singly bound oxygens get 3 lone pairs. There's the first structure, resonance arrow in between. Double bond on the right. And a -2 charge on the outside. Take a second, check yours. Do you have all 3 resonance structures? Double bonded all 3 different places. Take a second, catch up. Now what do I want to do? Well, I want to calculate the formal charge. Here's the good news. You only have to do this once, folks, right? You only have to do this once. Pick one of your 3 Lewis structures. I'll pick this guy. Okay, here's what we need to do. We need to calculate the formal charge for the central carbon atom. We need to calculate the formal charge for the doubly bound oxygen. And we need to calculate the formal charge for the singly bound oxygens. But you only need to do it once, because whatever the formal charge is you get for this guy, it's going to be the same formal charges for this guy. So you really just need to do 3 calculations. The central carbon, the doubly bound oxygens, and what the singly bound oxygens are, but you only got to do that once. So I want you to try that. Calculate the formal charge for the central carbon, and then each type of oxygen, and we'll talk. All right. We got a doubly bound oxygen here. That's going to be 6 minus number of bonds it's making, 2, plus the number of electrons in lone pairs, 4. That doubly bound oxygen is a happy little oxygen. It's rocking a 0 formal charge. Let's do the carbon. We got 4 valence electrons per carbon. That carbon is making 4 bonds, and it's got no electrons in lone pairs. That's also a 0. But hold on, folks. This oxygen, we got 6 minus number of bonds it's making, 1, plus the number of electrons in lone pairs. That's a -1 formal charge. Each of these singly bound oxygens has a -1 formal charge. So what do we got here? We got an oxygen with a 0, a carbon with a 0, and 2 oxygens with a -1. So what does that mean? Well, the sum of the formal charges is 0 plus 0 minus 1 minus 1. That's -2. So this whole structure has a sum of a -2 formal charge. That's actually good. Here's why it's good. Carbonate has a -2 charge. And the sum of the formal charges must add up to the total charge of the molecule or ion. This is an ion, so it's got a charge. So it's all going to add up to -2 anyway. So there you go. Carbonate. Cool. Let's try. Let me go back over COF2, which is what we ended class on Wednesday. When we did it on Wednesday, I told you that the reason it was the way it was is because nature loves symmetry. Now I'm going to be able to give you the real reason based on formal charge and what atoms are happier. So here we go. Let me draw that up here, and we'll get all back on the same page. No, it was COCl2, right? We did phosgene to end class, I think. So that's 4 plus 6 plus 14 equals 24. Take a second, get caught up. All right. So we're going to put carbon in the middle. We're going to have oxygen and 2 fluorines. Uses up 6 electrons, leaves me with 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. We're short 2. Now, on Wednesday, I told you that this was the best structure because nature loves symmetry, and this molecule has an internal mirror plane. The real reason is, and that's true, nature does love symmetry 99% of the time. The real reason is going to be formal charge. So what I want you to do is we're going to compare the two possible structures. So option one was to doubly bind an oxygen. What if we doubly bound one of the chlorines, though? So I'm going to draw another one of these guys over here. And I'm just going to doubly bond the chlorine on the right. Okay, so this is what the Lewis structure would look like if we doubly bound the chlorine on the right. Obviously, we could have done the left as well. Here's what I want you to do. I want you to calculate the formal charge on every atom on the correct structure where the phosgene molecule has the doubly bound oxygen. And then I want you to calculate the formal charge on each atom in the incorrect structure. Go ahead. Woo! What do we got here? Well, the structure that nature says, hey, this is a good one. That one has got a formal charge of 0 on all of the atoms. It is happy. It's happy. It's beautiful. Now, I only calculated one chlorine because that one's identical. So why do the same calculation twice? They're both 0. If we look at this ugly structure over here that nature does not like, we can see why it doesn't like it. The stablest structure is going to be the one with the lowest number of formal charges that still add up to the total charge. Well, phosgene is a neutral molecule, so it adds up to 0. So if you can get everybody at 0, that's good. This is a valid structure. The singly bound oxygen, -1. The carbon, 0. The doubly bound chlorine, +1. The singly bound chlorine, 0. All of the formal charges, -1, 0, +1, 0, they all add up to 0. It's a valid structure, but this is way worse than this one because everybody is 0 here, whereas this just adds up to 0 in the end. Way more stable structure right over here.